Hello class, welcome to chapter 9. It's hypothesis testing for one population. We also have hypothesis testing for two populations. That's the reason why we distinguish it here. For the purpose of this course, we will only focus on one population. Under chapter 9, we will look at 9a, which is basics of hypothesis testing. Let me give you the definition now. Because it's basics, this section will be mostly defining different parts or different terminologies in this hypothesis testing procedure. So bear with me if you don't get the full picture. When we begin to do a complete test, then you will know. So let me first introduce what hypothesis means. Hypothesis is a claim or a statement about a property of a population. I want you to again understand that the confidence interval section that we did, as well as this hypothesis testing, it's all in an effort to make estimations about the population. The population is the whole picture, and we have no way of collecting data from every member of the population. Therefore, we always deal with samples and use them as a best estimate about the population. Now, because of that challenge, we do have a lot of room for errors, in our estimation, because it's never going to be exactly the value of the population. But then how do we minimize the errors is one thing, and that's what we saw in confidence interval. Here, we're talking about testing a claim. So anybody can make a claim about a population. So if they make this claim about a population for which they don't have all the details, how do we know if what they're saying is true or not? And that is the reason why we have to approach this in a statistical, objective manner and make things clear if things were made in a subjective way, right? So people can make claims about things based on their feelings, based on their opinions. But how is it really the case with the population? Does it really reflect what the population says? So I want you to understand also some terminologies here. So property here would actually mean characteristic. So read again, claim about a characteristic of a population. What is the characteristic? Well, again, we can't make it subjective. We have to understand the population in numerical measurement terms, right? So we have, let me come here to the claim. So there are two ways, or rather three ways, I should say, three popular ways of making claims. So you can make claim about a mean. You can make claim about a proportion. We can make claim about standard deviation, okay, or variance. What this means is if we recall what we did in confidence interval section, we did go into proportion, right? And then there we saw this example of FB pages. So think of that, FB pages, 43% adults. Let me do a quick recap on that. There was a claim that was made saying that 43% of adults have an FB page, okay? 43% of adults have Facebook page. So this is a claim, right? And this claim is to do with the proportion, because we're telling what percentage of the population behaved in a certain way or had a certain characteristic. So the percentage here is the big pointer to the fact that we're talking about proportion. Proportion is a very commonly used one in media because it's more a survey type, it's more qualitative, and it helps us to understand opinions of people. It's used for polling to understand, is this an opinion in a certain geographical location, or is it how the entire population of the United States feels? So you can use all these things and statistically verify those claims. And so each time you see percentages, you know that it's about the proportion. claim about the mean. So we can say the mean wait time for in a McDonald's restaurant is 90 seconds. Okay. So if say, let's say the company makes this claim, okay, the mean wait time at our drive-through lanes is 90 seconds. So if they make that claim, is that true or not? That's one thing. But if you look at the claim itself, the claim is about the mean time, the average wait time, right? And so you can see that that was the characteristic they were talking about. So we can talk about McDonald's mean wait time in drive-through. Okay, so think of it. So they make a claim, and that claim we want to see. Now I made this up. Okay, so I don't know, they didn't really make that claim. They probably make some claims, but not the one I'm trying to use as an example here. So I'm saying the mean wait time is 90 seconds in the drive-through. Okay, this does not sound realistic, but just for us to have some number. So if you were to convert these things to statistical notations, then I would say the mean wait time is 90 seconds. So notice that this is the mean. So I'm making a claim about the population, because I didn't say where, I'm just saying in general, any McDonald's drive-through, the mean wait time is 90 seconds. Okay. Now, if I said the mean wait time is more than 90 seconds, then that would change the equality to an inequality. And it says, oh, the mean wait time, the population mean, right, is more than 90 seconds. If I say the mean wait time in McDonald's drive-through is less than 90 seconds, then I put that all in mathematical terms or statistical terms, right? Now, when we talk about proportion, what was the population proportion? The symbol for population proportion was P, okay? So when we say 43% of adults have Facebook page, then I'm saying P, which is the population proportion, all the adults, then I would make it as 0.43, okay? Now, if the language said at least 43% of adults have Facebook page, at least means 43% or more, okay? Then I would have the greater than or equal to symbol to represent that information. And if I say at most 43% of adults have Facebook page, at most would mean that that's the maximum. So it was less than that. It went as far as 43%. So then it should be P is less than or equal to 0.43. This is what you're going to learn in this, the rest of this chapter, where whatever is given to us in words, we're trying to translate it into statistical terminology or into statistical notation, and then turn it into a math property. And then from there, we will be able to statistically test these claims. Okay, so that was a hypothesis. What is hypothesis test? So because this can get subjective, we make sure that this is done objectively, right, without any bias. And so we use statistical procedure. So it's common to all, it's uniform to test a claim, okay? And it's also known as test of significance. Now, if you think of significance, remember in stats, we use this whenever we have any unusual results, right? And a quick way to recall that was, remember we said if you went 2 standard deviations away, that's your mean. This is 2 standard deviations. So if you went away, I went away. Okay. So if you went here or here, which was outside the 2 standard deviation mark, it shows that it's unusual because 95% of your stuff should fall in within the middle portion. If all your data values fall outside the 2 standard, that was the rule of thumb. But with hypothesis testing, we can make it as stringent or as relaxed as possible, depending on the context of the problem. This rule of thumb is in general, 95% of your data values will fall in the middle. And so if you had that extra 5% that's falling on the tails, 2.5% on the left and the 2.5% data values on the right, those are unusual values. They can be, we need to investigate them. Are they really outliers, or do they mean something because they are in the unusual zone? And so we are using hypothesis testing in a similar fashion to see what that borderline will be, right? 2 sigma is the borderline in general, but in a particular context, what would be the borderline? In fact, we saw that in confidence intervals. When we found Z alpha over 2, T alpha over 2, we were trying to position that borderline to separate what was significant from what was insignificant. So anything that's unusual is significant, right? And so the shaded portion here is the unusual portion. And that is what we mean by test of significance, to determine if the claim was significant or not. Now for this, to give you an understanding of this procedure, I'd like to kind of show you the big picture, you know, the bird's eye view. Now, because this is a statistical procedure, as you can see, we have 7 steps, or rather 8 steps, because the 8th step is the interpretation of your results. So we have these steps to follow in sequence. As you can see, the flow chart shows you how to go from one step to another. And these are pretty technical. So my job here in this section is to give you the meaning or the terminology for each of these steps, so that when we do an actual problem, we will be able to assemble them meaningfully and cohesively as we go through from one step to another. Okay, so let me just run through it. When you are given a problem, the first step is to identify the claim. That's what it says here. Then once you identify the claim that is in English, then you want to replace that English into symbolic form, into mathematical or statistical form. So that is step 2, converting from English to stats or to math. The third step says, identify the null and alternative hypothesis. Now we haven't seen what this is. We don't know what this is. So I will be explaining that. And then once you have identified them, then we will select significance level. Again, this is something I will explain, but you kind of have an idea. Significance level, you remember confidence level? Significance level is the other side of the it's a complement of the confidence level. If confidence level is 95%, the significance level is 5%. So that is what we're talking about here. So significance level will be the alpha that we used in the confidence interval topic. Then we identify the test statistic. Okay, this also we saw a glimpse of it in confidence intervals, the Z alpha over 2, the T alpha over 2. And there's also one more, chi-squared. We didn't see that, but chi-squared is used for standard deviation or variance to test claims about standard deviation or variance. Then we have 2 ways. There are 2 ways in which you can test the actual testing to see if it is significant or not. So we have something called the p-value method, and something called the critical value method. P-value method is used mostly in using the software or calculator. Critical value method is more visual. You draw a graph in both places you draw the graph, but critical value kind of indicates to you the critical region and all that. So you can do both of them using software, but p-value is mostly used in most calculations. And then finally, whatever method you use, you should arrive at the same decision, right? Because they're equivalent methods. And the 8th step says we have to now explain that decision or restate the statistical decision you took in step 6 and step 7 In step 8, you're going to write it in non-technical terms so that laypersons can understand how you have addressed the original claim. So these are the steps we will follow in order to test a claim. So let's get back to understanding each one of them. To help us walk through this with a context, I will write down this problem for you so that we can use that problem as a way to make reference to this to these individual steps. Let me read the question to you. 1,009 consumers were asked if they are comfortable with having drones deliver their purchases, and 54%, or 545 of them, responded no. Test the claim that the majority of consumers are not comfortable with drone deliveries. Okay. If I recall right, I believe this was an experiment that Amazon conducted in UK. I'm not able to verify, but I think I've read something to that effect. So now, given our coronavirus circumstances, that wouldn't be a bad idea. All right. So if you look at this question again, 1,009 consumers were asked, and among them, 54% of them responded no. But the claim says the majority of consumers are not comfortable with drone deliveries. If you understand the language here, you will see that they found some information from the sample and used that information to cast it upon the entire population. The entire population is all consumers, okay? Let's assume this was to do with Amazon. Then we're talking about all Amazon consumers all over the world, right? Even if they had restricted the population to all of UK, still we have not asked every consumer in UK about the possibility or about how comfortable they are with drone deliveries, right? But the claim is saying that majority of the consumers are not comfortable. And that is a claim on the population, right? Majority of consumers. But then we have a sample, 1,009 consumers were surveyed and they gave some responses. Okay. So here we are going to first identify the claim. Okay. So that's the first step I want to identify the claim. The first step I want to explain here. It's kind of easy in this problem because they kind of gave us the hint. It said test the claim that, so you know, the following information is the claim. Nevertheless, we understand the claim is that majority are not comfortable, okay? Not comfortable is the theme here. So there are two categories, not comfortable and those who are comfortable. But we're not focusing on those who are comfortable. Indirectly, we know who is not comfortable. But directly speaking, we are interested in those who said no or who are not comfortable. Okay, majority of consumers. So you have hint here that 54% of them responded no. That 54% draws your attention to the fact that they're talking about proportion. The claim is about proportion. Also, you can see that the fact that they mentioned the word majority also indicates a proportion. Majority is most of them. So how do you know what the majority is? Excuse me. For that, first I want to understand that this is proportion, population proportion. So the symbol for that is P with no hat or prime. Population proportion, P, indicates the proportion of customers who said no, right? Or who said they're not comfortable. So P is proportion of all those customers or consumers. Majority means more than 50%, right? More than 50% means you have a majority. And that is the indirect information we will use, more than 50%. So it's not equal to 50%, then that would make it 50-50. We want majority, so that we want more. And the way we write that is greater. 50% is 0.50 or 0.5. So identify the claim. So first I would like to write that in English, okay, what I identified as the claim. So the sentence for that is majority of consumers are not comfortable with drone delivery. Okay. And once you identify it in English, then put it in symbolic form. And that's what we just did when I explained it there. So you come back and you say, okay, majority means more than 50% of the consumers, right? And then consumers here means all of them, which implies we're talking about the population proportion. Once you have these two details, then you're kind of assembling them as P, which represents population proportion, more than, which is greater than, 50% is 0.50 or 0.5. And so this is your claim, right? Then we can talk about let me quickly take you to the third step here. Third step here says identify null and alternative hypothesis. So let's come to that. Null hypothesis. Null means zero, right? No. So the symbol for that is hypothesis is H with a subscript 0. We call it the naught. Okay. So I will say read as H naught. It's not NOT. It's the old English naught. Okay, but that's actually means NOT. Okay. So H naught is the notation we use for null hypothesis. You can't go wrong with that, right? Null is the 0 and a hypothesis is H. So null hypothesis. What does this mean? Again, we're trying to put all this in statistical sense. So this is how we define this, okay? Statement, it is a statement about a population parameter Remember, population parameter is a population characteristic. And from what we know, we are using P for proportion, mu for mean, right? Population. Just think of that. It's a statement about a population parameter that, oops, switch the color, that is equal, that's the key part, equal to some claimed value. Okay. So you know that your claim in the previous step was P greater than 0.5. Null hypothesis says, no matter what that claim is, you will always write your H0 statement with an equal sign, simply. Okay. It has to have an equal sign. It cannot have an inequality, even though the actual claim has it. And if you think about this, you want to either accept, I mean, I shouldn't say accept. You either want to reject the claim or fail to reject the claim, okay? Because we can't accept it fully, because we never can confidently, 100% confidently say, yes, this claim is perfect. Because we never know fully about the population, so we can never openly say, yes, we accept it. When we say we fail to reject it, we are kind of accepting it, because we're saying, well, we have no other choice but to fail to reject this. In some sense, we are able to accept it. Anyway, so coming back to the decision would be, do I reject the claim or do I fail to reject the claim, is where it stands. For that, you should have an opposite view, isn't it? And that is the reason why we have to develop statements based on the claim, but in a certain format. So according to the definition here, I'm going to readjust my H0 so that my population parameter used here is P, right, is equal to some claimed value. The claimed value is 50%, majority. The claimed value is 0.5 in my case. So I have rewritten a null hypothesis by setting my population proportion equal to the claimed value 0.5. So simply put, null hypothesis must always have the equals sign. The other one is called the alternative hypothesis. An alternative is an alternative to the null, right? So it should be the opposite. So these two must be opposites. Now, the way we represent this also is with an H, but the suffix or the subscript would be HA for alternative, or sometimes it's called H with a lowercase a, because in math it's case sensitive, so sometimes it's a lowercase a, and sometimes it's simply H1, okay? Because it's seen as a 0. If you're seeing it as mathematical expression, then H0, H0, and H1. Okay? These are different ways you can express the symbol. So you read it as HA, H1, and so on. What about this? It's hypothesis. So this is also a claim or a statement, right? So this is a statement about a population parameter, same thing. And you could also use sigma, but we're not doing that in this course. So in this section, so I'm just using the P and the mu. That it is somehow different from the null hypothesis. That makes sense. If it's alternative, it has to be something different from the null. And so what could be the opposite or different from the null? So the null could be, the null is always equals, right? It's always equals by default. So the opposite of equals, you can have any one of these symbols, okay? So, so I'll just say opposite of equals could mean any one of these. It could be that if it is equal to 0.5, then the opposite could be that it's less than 0.5. If it's equal, if null is equal, then the opposite could mean that it was greater than 0.5. So you could use that as the way to be different from the null. Or it could simply mean not equal to. Excuse me. It could simply mean not equal to, right? So your null, your alternative hypothesis will utilize one of these three inequality notations, symbols. Now, if you come back to our question, the opposite in this case to the null is actually a claim, because a claim says P is greater than 0.5. So it is not less than, it is not equal to, but you have a specific symbol that you could use because your claim speaks about that. The null hypothesis does not care about the claim, it cares about the claim value, because null hypothesis by default takes the equals. So it doesn't matter what inequality you had, even if you had equals in your claim, your null will still be that equals. Okay. Again, when we do a complete problem, you'll see how it all falls in place. So then I have my H1. I'd like to use H1, so I'm just going to use H1. H1 is my statement where I'm saying P is greater than 0.5. So your null hypothesis always has equals, alternative hypothesis never has equals. So anything other than equals. So it's less than, greater than, less than, equal to, greater than, equal to, or not equal to. But if I had less than equal to, Let me just quickly show that. I accidentally said less than equal to greater than equal to. The problem with that is you have the equals bar, so you can never have these in your symbols. So it has to be strictly less than, strictly greater than, and not equal to. So I apologize for going with the flow there. So you cannot have the inequality with the equals bar. It has to be strict inequality. All right. So we got step 3, right, which is getting your null and your alternative hypothesis. The next step was, maybe I should just write the steps, right? That'll be easier. So I'm going to do that here. I just say step 1, because you have the 8-step process. It will be helpful to write it as steps right away. Step 2. And these two together constitute step 3. And so step 4 is significance level. And that is your alpha, okay? So quick way to remember this is, remember we did the confidence interval, and alpha are complements, not complement. Complement means, you know, you have a nice word for someone. The complement means they are kind of opposites, okay? So if confidence interval was 95%, then alpha was 5%, remember that? So here our focus is not Ci, because we already took care of that in the previous chapter. Our focus is alpha, okay? So if you're 95% confident, then you are 5% not confident, right? So that is where you're really interested in seeing the significance, because that's where it's significant, right? Because it's the tails where it can mark the borderline between what is significant and insignificant. So alpha comes in really handy here, okay? If I were to put the definition of significance of alpha, then it's going to be a little lengthy, but you want to see that, you know, the probability, alpha is a probability, right? So I'll just write that here. Probability so your alpha can only be between 0 and 1 if you're writing it in decimals. That's why we always write it in decimals, to keep that. We never, even if it's percentage, we convert it to decimals so that we stick to the between 0, 1 condition. To give you the definition, right? Alpha is nothing but the probability of rejecting H0, the null hypothesis, when H0 is true. It's a different way of thinking, but if you think about it, it is meaningful. Now say H0, let me come back here, okay? The claim they made was that majority did not like, were not comfortable with drone delivery. If you come to the null hypothesis, how do we interpret this? This means that there were equal number of people who liked it and equal number of people who did not like it, right? That's what it means. This equal 0.5 means 50% did not like drone delivery, the other 50% liked the drone delivery. So you really cannot make a significant claim here because it's 50-50, right? So if this was true, let's say 50%, not majority, but 50%, half of them liked it, half of them didn't like it. If this was the truth there, then if you come down to alpha, alpha is saying it's the probability, what is the chance that if H0 was true and we rejected it? That means you'll be accepting the claim falsely, isn't it? And that is what this alpha is helping us do, to see or minimize that error. The error of rejecting H0 when H0 is true. And so alpha helps us to understand that significance level. So the whole test, if you see, is based on the null hypothesis, because the null hypothesis is kind of turning your claim into a neutral setup, right? Because you're saying it's equal to. So you are giving it a point. So you're keeping it neutral, and then if H0 is true, we want to make sure that we understood that and not reject it. And if H0 is not true, we want to make sure that we reject it. So alpha helps us to make that decision in the end. For now, this is how we understand. Alpha is the complement of confidence. Okay? 95% confidence means 5% is where it can go wrong, the error. And that is what we're trying to understand. Anyways, alpha, commonly used alpha values are the 5%, 0.05, 0.01 for the 10%, and 0.10 for the 1%. I apologize, I mixed it up. 0.01 is for the 1% and 0.10 is for the 10%. Let me write that down here. This is 5%, this is 1%, this is 10%. 10% seems like too much, right? You're allowing too much error, but again, it all depends on the context. So these are the common alpha choices. Step 5. It's called the test statistic. Again, statistics means the study of collecting data, analyzing it, interpreting it, all that. Statistic is the term we use for the characteristic of a sample. Okay, we're not dealing with samples. All along, we were talking about how to set up the claim or the statements for the proportion for the population. But here we're going to talk about for the sample. Okay? But we're trying things in general, so I'm not really particularly sticking to proportion, but our example is to do with proportion. So here it would mean sample proportion, p hat. If our example was about estimating or making a claim about the population mean, then this test statistic would be about sample mean. So please keep that very clear. Okay. So let's say test statistic is about the sampling distribution. Please understand it's the sample. Okay. And in sampling distribution, we saw normal, right, the Z, or the T distribution, normal distribution, T distribution. If you haven't seen this, it's called the chi-squared. Don't worry about that. Chi-squared is actually the test we use for standard deviation or the variance. So for this, I'm going to take you to the screen. Here again, we are in this 5th step, okay? So how do we know when to use normal, when to use t-test, and when to use chi-squared? Well, again, we're not looking at chi-squared, so let's just focus on these two, when to use normal and when to use t-squared. So we have this table that will help us to understand this. Okay, when we begin to look at problems, you'll use this table much more. This table is a collection of all the formulas as well for the test statistic. The last column you see here is the column of interest. Okay. And these 3 columns that go ahead of it tell us when to use it and what requirements should be checked in order to be able to use it. Okay. And because our example is about proportion, you notice that for proportion we use normal. Okay. We have no confusion there. The only confusion I would say, not confusion, the choices would be that if you went with mean, for mean you had 2 options. Could be either the T or the normal because you have 2 separate conditions. If you look at the formula here, the T formula is x bar minus mu over S over root n, and here it will be x bar minus mu over sigma over root n. So that's the only difference. It's not so different, but it is significantly different just because the S is to do with the sample standard deviation. We saw that in confidence interval, right? That's the sample standard deviation, and sigma would be the population standard deviation. If you have sigma known, which is very rare, If sigma is known, then we use this. Or if you know that it was from a normal distribution. Okay. So you use sample SD when sigma is unknown. Okay. All right, we'll come back here. So the test statistic, as far as our problem, our example is concerned, would use, oops, I'm sorry, would use the P, or in this case, it would use the Z test, right? So I'll say proportion P has, of course, you have to do all the requirements and everything, but this means we are using normal, the Z, right? And Z here means your formula is P hat minus P, P hat minus P over square root of PQ over N. Okay, that's the formula that's given to us. Again, remember what your P hat and all those things stand for. Let's write that here. P hat is the sample proportion. P, without any symbols on it, is the population proportion. Q is obtained by doing 1 minus P, and N is the sample size. How many members or items or values are in your sample. Next, we have the mean, population mean, mu. If you are using the t-test, t-distribution, the formula is t equals x bar minus mu over s over root n. Again, if you recall, this was your CLT, central limit theorem. So the variables are x bar, x bar stands for sample mean, mu is your population mean, S is your sample standard deviation, and N is your sample size again. With sample standard deviation, if you are already given that information as part of the problem, well and good, because you could just plug that in for S. If you are given a data set, you have to use your calculator, punch that in the list, and then use your vars, right? Stat button to get your to get your details or your results on X bar, S, and so on, because you will not then need X bar as well as S from your data set calculation. If they are given to you directly, well and good. Okay, and then the other one was if you had the sigma given to you, then this S will be replaced by sigma. Because it's a very rare, it's very rare that one would be able to give you the population standard deviation without knowing what the population mean is, then we don't really use the normal version of it. We always use the t-distribution version of it. So these are your test statistic, but for our example, we would have used the Z. Okay? So let's go ahead and do this for the example. So I want to make sure that we are doing this specifically to the drone example. So for the drone example, your test statistic, let me write that in words first, is Z equals P hat minus P over square root of PQ over N. Now you need to plug all these values for which you need to collect your variables. So p hat in our drone problem, p hat is coming from the sample, the 1009 folks who were surveyed, right? So we got that p hat is always your x over n. X represents the number of successes, right? In this problem, the success is all those who said no, because that is our focus. Whatever is your focus is your success. So don't always think success has to have a positive result, okay? So in this case, success means the number of consumers who said no. Who said no. And remember, that is your number of successes. Okay? And n is your sample size. So let me just write that as total number of people surveyed. That is your sample size, isn't it? Now, they did give us these details already as a percentage, but they also gave us 545 were the number of people who said no, they're not comfortable, over 1009. And the percentage they gave us was 54%, right? And that's a rounded version. So if you did the fractional version, then your actual answer comes out to be 0.540138875. So you get a longer number, right? Because they gave us 0.54, 54%, we can round it to 0.54. Okay. All right, so that was a p hat. P is the claim. P comes from the claim. So P is 0.5, right? That comes from your claim. So P is 0.5. You can see it in the null hypothesis. You can also see it in step 2 in your claim. The claim was majority. Okay? But then from the majority, you understand that it must be 50%, more than 50%, but P is equal to 0.5. This comes from the claim. Okay. Once you have P, then you have Q, which is 1 minus P, which is also 0.5. We have all the details we need, so let's come back here and plug it in. So 0.54 minus 0.5 divided by square root of 0.5 times 0.5 divided by 1009. Please do not round beforehand. Use a calculator to punch them all in, and the final answer is what you want to round. Okay? Because this is a z value, you will be using the table, right? If you're using the table. If you're using the calculator, well, it does things for you. But if you're using the table, that's how I'm going to explain it here, because I can't show the calculator. I'm going to use the table. In the table, take a quick look at the table. In the table, if you recall, I used this in the previous example, your z values go only up to 2 decimal places, right? And for that reason, we will also remember to use 2 decimal places or round to 2 decimal places. So this will be rounded to 2.54. We will need this information when we draw the graph, because remember your z is a value on the z scale. So we're going to position this 2.54 on that z scale and see, use that as part of our test now. But we're still in, what are we, step 5. We're in step 5. Okay. Let's go to the next one. Step 5 is identify the test statistic. Step 6, you branch out into 2 methods, right? One of the 2 methods. So we're going to look at each method and then move on to the next step. Okay. All right. So we'll start with the critical region. Okay. So I'll just say step 6 has either the critical value, is either the critical value method that you use, or the p-value method. A lot of p's that we use here, but remember this is p-value, capital P is the way we present it. P-value, in some places they use small p as well, but this is the probability value, okay? So this is a value that you will compute. So remember it's p-value method, and that is different from the other p that you have seen before. Okay? It's the probability of getting a value of the test statistic. All right, so let's focus on the critical region. Maybe I could divide the page here. You can see both options. So critical value here says, so for that we need to talk about critical region. Let me define that first. It's also known as rejection region. This is interesting because now you actually begin to see what region it is that we will use to decide whether the claim should be rejected or not. Region, therefore it is the area, right? It's a region. So it's the area corresponding to all values of the test statistic that causes us to reject the null hypothesis. Remember, our focus is whether to reject the null hypothesis or fail to reject the null hypothesis, because once you do that, you know, the alternate, if you reject the null hypothesis, then the alternate hypothesis holds true. If you fail to reject the null hypothesis, then the null hypothesis itself holds true. So we are holding the standard with the null hypothesis. So that's the reason why this is the area that corresponds to all values of the test statistic that causes us to reject the null hypothesis. And there we have two-tailed, left-tailed, and right-tailed regions, right? Your region could be in any of those. So let's talk about that. Two-tailed. I'll show it to you through a visual so it's easy for us to see what that is. This is your mean. Two-tailed, as the name says, if you have two ends that are shaded, then it's two-tailed. How do I know? I have to use a two-tailed test. I should say test, two-tailed test. So if your H1, your null hypothesis, if that uses a not equal to, then we use two-tailed test. Okay. When we get to the test, I'll tell you what that is, but we use the two-tailed test, which means you are shading both the tail ends, okay? Left-tailed test. You will use this when you are only shading the left tail. Still your mean. And then this is the region that you're shading. And that will be when your H1 uses less than symbol. Less than left, right? Easy to remember. Then lastly, the right-tailed test. is when you shade it on the right end. And so H1 uses greater than. Greater than is bigger, so it's on the right. Now, if you go back to this table, especially the T table, right? Let me remove all these things because we used it for a different lesson. I apologize. Okay, here you can see actually the language of one tail, two tailed. It says one tail, two tails. So to know which one to use, to know which value or which row to use, we need to know if it's one-tailed or two-tailed. So it becomes meaningful, significant when we identify this, right? So we will also need that in the Z table, okay? When we know if it's two-tailed, then roughly to give you an idea, you have to find the answer multiplied by 2 for one of the tails. You find the answer for one of the tails and multiplied by 2 because you have two tail ends. If it is just the left end, then you can use the table as it is because it's cumulative from the left. If it's a right end that is shaded, you have to remember to do 1 minus that right shaded area to get the cumulative area from the left. So those are the things you will remember in the when you have decided whether it's two-tailed, left or right-tailed. Sorry. What happens next is the p-value method. That is right here. Well, we'll first define this because there are a lot of p's, and let's define what this p stands for. It is the probability of getting a value of the test statistic that is at least as extreme I'm going to emphasize that, as the test statistic obtained from the sample data. Assuming that the null hypothesis is true. Read it again. The probability of getting a value of the test statistic that is at least as extreme as the test statistic obtained from the sample data. So if you go back to the previous step, right, we got test statistic 2.54. Okay? So this p-value is obtained from the table, and we want to see if that table value or the calculated value from the calculator, if that value is at least as extreme as this value you got from step 5. And this is with the assumption that the null hypothesis is true. Again, when we do a problem, you'll begin to see that this all makes sense. Okay. Maybe, yes, and we'll try to do the drone example here. Okay. So if you come to our drone example, let's go to H1 because H1 will tell us, where are we? Here's H1. Okay. H1 uses the greater than symbol, right? If it uses the greater than symbol, according to critical value method, this would be a right-tailed test, isn't it? So you will only shade the right end of the tail. Now, if you are using the p-value method, then we have to use the table, okay? So this is a right tail test. Let me write that down first quickly. So for the drone example, under the critical value, it would be right-tailed test, since H1 gave us P greater than 0.5. So it was a greater than symbol. That made it the right tail test. If you're using the p-value method, okay, we have hold on. What was it? 2.55. Hold on. I forgot the z score. Okay, 2.54. Okay. So the z value, the z statistic was a right tail test with 2.55, right? You could use a calculator for this one and use technology to get the p-value. The p-value will come out to be 0.005. Here. Okay, well, because the technology gives you with a 5.4, and you can round it to 0.005. Again, I will save this calculation for later when we do the actual problem. Okay. We can move to the next step. So this p-value, I use the calculator to quickly give you a gist, but I wanted to show you how to get the p-value, okay? All right. So there is like this flow chart that tells you how to find the p-value. So let me just write that somewhere here. Finding p-values. So we have to decide what type of test it is, and we just saw in the critical region that the test is right-tailed, right? And if it's right-tailed, then you go to the test statistic, right? The test statistic, if it is right-tailed, we have the p-value that is equal to the area to the right of the test statistic. And then we also see where the test statistic lies, okay? Does the test statistic lie on the left or the right of the center? And then that gives you p-values twice the area of the right of the test statistic. Okay. So p-value is, we are focusing on this, right? The right side, because it's the right tail test. And using that procedure, where are we? We come down to finding the p-value as 0.0054. Again, I will save this for later, okay? With the critical value method, it's kind of easy because we just use the alpha to determine the z. So let me, because I don't need to do the calculations as such for that. So I'll just use the drone example for just the critical value here. What happens here is you have the graph, and we establish that it has to be right-tailed. We have that, and we need to find this border value. And if you use alpha, the commonly used alpha, which is 0.05, it was not given in the problem, but if you use a common value, 0.5, we know that its corresponding z alpha over 2, right, was 1.9, no, z alpha, I apologize, it's not alpha over 2. So z alpha, or z, would be 1.645. Let me see if I can pull that from the table here. There was a z thing here, but I was wondering if I can use that. Okay. No, okay, that's fine. You can also come here to this one instead, okay? And you could locate 0.05, okay? And because it's right-tailed, you expect your z value to be positive, okay? And because it's right-tailed, it's 0.05. I'm just jumping here and there, I'm so sorry. This is 0.05, right? That area. If that area is 0.05, if you go to the table, the table gives you the cumulative area from the left. So that has to be 1 minus 0.05. That is 0.9. Apologize, there was some audio issues. Okay, I think we're back. So where was I? 1 minus 0.05 is 0.95. So then you go to the body of the table, and where's 0.95? Well, this seems to be the closest. Let me highlight that. So it's between this, oh, wrong one. It's between this and this, right? So 0.9505 seems to be the closer one. So look at its corresponding z-score. It's 1.65, right? 1.65. But if you use technology, or if you use the table, well, this is a t-table, but I'm just saying, if you use a table that has those values already, you can use the 1.645 value. But this was against 90% because you're looking at the wrong table. But I just wanted to show you that you have more decimal places in some charts. Or if you're using calculator, it gives you the more accurate value. All right. So the z value here, right? You're not using the alpha over 2. That was different. Okay, the z value here, because it's alpha over 2 was divided over the two tails. Here, everything is taken up by one tail because we decided it was a two-tail test, a right tail test. Because of that, the entire 0.05 or the 5% area lies on the right. So z is 1.645, okay? And then the z that you got from step 5, yeah. The z we got from the drone example of step 5 was 2.54. And you have to see where this lands. In our graph, 2.5, this is the 0, right? Z equals 0. That's 1.645. So 2.55 or 54 is going to lie in this region. Right? That is the test statistic from step 5. So step 5 lands inside the yellow shaded region. That's the critical region or the region of rejection. And therefore, we will make some decisions based on that. Again, I'm not going to go into too much detail, but it was easier for me to explain this for the critical value, and therefore I used that here. So the test statistic fell in the region of rejection. We go to step 7. Step 7 was here. It says make a decision. So under p-value method, it says these are the guidelines to either reject or fail to reject under p-value method and for under critical value method. Okay? I'm just going to do that here. Make a decision. So that will be critical value method, and another column for p-value method. Excuse me. So we will reject the null hypothesis. Remember again, it's all about H0. So reject H0 if the test statistic is in the critical region. The shaded region, right? Fail to reject H0 if the test statistic is not in the critical region. So it's a little more visual, right? Notice we did not say accept H0, we said fail to reject H0. And for the p-value, you have to make similar decisions. So we reject H0 if p-value that you determined was less than or equal to alpha, and fail to reject H0 is the other way around, if p-value is greater than alpha. Okay. And lastly, step 8. I will just say interpretation or restate. Restate decision. And you can't just use your own words to interpret this. You'll have to use standard language and then insert the context into it to interpret. So there is actually a table, okay? I'm going to show that table to you for this step. So this is how you speak. Okay? These are the conditions, the first column, and the second column gives you the conclusions. If the original claim does not include equality and you reject H0, then this is how you have to conclude. There is sufficient evidence to support the claim that, and then you will continue on with the context. Okay? So for instance, if we are using the drone example, there is sufficient evidence to support the claim that a majority of consumers are not comfortable with drone delivery. If you go for the second one, original claim does not include equality and you fail to reject H0, then you will say there is not sufficient evidence to support the claim that the majority of the consumers are not comfortable with drone delivery. So you finish off with a sentence that comes from the question, but this is how you will say. You will say that there is evidence to support, or there is not enough evidence to support. Then you will say there is evidence to warrant rejection, or you will say there is not enough evidence to warrant rejection. That's the language you have to stick to. For our quick understanding, remember, the original claim, I wanted to say claim, does not include equality. That means your original claim is sitting in H1, and we reject H0. This is how we decide, okay? If your, once again, if your claim does not include equality, that means your claim is in H1. your claim itself is your H1, and you fail to reject H0, then your conclusion should read that. And if your original claim does include equality, if it includes equality, it definitely must be the H0, because that's the only place where you can have the equals. And if you reject H0, then there is sufficient evidence to warrant rejection. And lastly, if your claim is in H0 and you fail to reject, then there is not sufficient evidence to warrant rejection. So notice how the language is very careful. Please maintain this language. All right. Then we have something called type 1 and type 2 errors. So I'll just give you a quick description on that. We're technically done with all the steps of hypothesis testing. I need to just talk about type 1 and type 2 errors because it's really important. Type 1 error, so I'll just put it simply. Type 1 error is the alpha, okay? Alpha is the error, right? Because that is where, remember the confidence interval and alpha, how they're related? Confidence interval is the confidence. So if 95% confidence interval has an alpha of 5%, so 5% is where it can go wrong. That's where the error could be. So alpha is the probability of that type 1 error. Type 1 error. And if you recall, type 1 error was, alpha was rejecting H0 when H0 is true. Right? Think of this as false negative, right? False positive. It's especially relevant here in these coronavirus days, where a person may not show any symptoms, but they may be actually carrying the virus, right? So that is a false positive. So they're showing that they are, well, here positive, negative is subjective, kind of. So positive in the sense that they're fine, but they actually carry the virus. So if you're changing that to medical terms, then they would call it false negative, because their tests would have, they would have thought that they didn't have the virus, so negative in that sense. It just depends on how subjective it is in how we define positive and negative. So anyways, what I'm trying to say is a person who may have symptoms, maybe coughing and all that, but when you test them, they may actually not have the virus. The symptoms could have been caused by other factors like allergies or other conditions, asthma or things like that. So that is the type of error, right? So you have the false positive and the false negative. And that's what we're trying to minimize. We're trying to minimize those errors. So the type 2 error here would be beta, which is probability of type 2 error. And you can think of this as failing, probability of failing to reject H0 when H0 is false. See? So if you want to put this in a chart, right? If H0 is false and you reject it, is that good or bad? Well, it is good. It's a correct decision. If your H0 is true and you fail to reject it, that means that's a correct decision. But if you did things the other way around, then that's when you have the error, right? So let me see if I have a chart on that. Yes, I do. Okay. So these are correct decisions, right? because you're rejecting H0 when H0 is false. Reject when it is false and fail to reject when it is true. So again, using coronavirus as the example here, if they tested and they got it false, like they did not have the virus, then we are sending them away, right? No treatment, so they're fine. That's correct decision. Now, if they were tested that they were that they had the virus, then we fail to reject, meaning we do not want to send them away, we treat them, right? So then that's correct decision. They had the virus, we treated them, and then they didn't have the virus, we did not treat them. Good. Now, if they had the virus, okay, and we did not treat them, that is bad. That is like your type 1 error, right? And type 2 error is like when they did not have the virus, but they were treated. You can kind of see which one is more serious, right? Type 1 seems to be more serious than type 2 because they had the virus and we did not treat them. That is type 1 error. Type 2 error is they did not have the virus, we still treated them. All right, and I think that's about it for our 9A. And so again, this was all about terminology. So, and we kind of explained each step to you. In the next lecture, we'll be doing actual context problems where we will do all the 7 steps and then make an interpretation with the 8th step using non-technical terms. So I will see you in the next video.